If you're into 3D printing, you should know, if you don't already, that keeping your filament dry is one of the most important factors to getting really good high quality prints. And this goes for all filament types with the likely exception of PLA. And PLA happens to be the material that most people are printing with anyway, so that's why we don't hear about drying filament all the time, because really it's a major issue. And for me, I like to print with higher temperature and higher strength plastics other than PLA, and that's why I made this filament dryer in a previous video. And this is basically just the guts out of a food dehydrator, and I installed it into this sonotube. That's a concrete form tube here. You can buy these at the Home Depot or Lowe's or your hardware store of choice. And I've got all these internals here that just help kind of direct the airflow. And it does work. It gets up to 150 degrees and it circulates the air. So sometimes I've got to run filament for like 12 hours. A large part of the reason for that is the perforations or lack thereof on the filament spool. So this is the way that it should be, with lots of air able to flow through the sides of the filament spool. And this is the way that it should not be. Unfortunately, many filament makers make spools like this. The reason is because they're heavier. So they can sell you a kilogram of filament and it's mostly spool, whereas this is a lighter weight spool, so they're giving you a better value. So if you want to just judge filament quality based on spools, this is the stuff to get, when it looks like this. So yeah, I do have some issues getting my filament to dry. It just takes a long time in this little mini oven. But after it's all dry, I tend to store it in an airtight container. Now I got this one at, again, the big box store, Lowe's, Home Depot, that kind of thing. But basically they sell this as like a dog food container, and it's got a nice seal around the lip, and then the lid just screws right back on. And this whole lid thing, it's not cheap. It's like 20 bucks, I think. But this whole lid just screws right on like so, and the whole thing mounts onto a bucket. But that is a really good airtight container. The combination of these things mostly keeps my filament dry. But there's a problem, because there's a process called hydrolysis, where the water molecules break apart the chains of the plastic molecules. And so it happens to be accelerated when you cook the filament that's wet. So some plastics, being dried in an oven, will chemically change the properties of the plastic, which is no bueno. So the ideal way to dry your plastics would be to freeze dry them. And that is why I bought a vacuum pump. And I got this one for like $50. If you go down to like your Hazard Fraught, you're gonna pay like $100 to $150 for one of these. But go on to the usual suspects for cheap crap from China, and you'll find one for 50 bucks, which is awesome. So we're gonna use this to make a vacuum filament dryer. We're gonna modify this bucket and suck all the air out of it and more or less freeze dry our plastics. So let's roll that intro and start the project. Let's take a quick moment to clarify exactly what it is I'm trying to achieve with this vacuum filament dryer. So freeze drying, something we've all heard of, probably because of food. Here's some astronaut ice cream that was freeze dried. And the way that they made that is they took ice cream, they froze it, then they stuck it into a freeze drying oven, which is literally a vacuum chamber with heated trays. And so as the ice cream gets hot, it never melts because the air is missing from the chamber. And so the ice goes instantly from a solid to a gas. And the heat is transferred from the trays to the ice cream through conduction, because the ice cream's sitting directly on the trays that are heated. And also there's a little bit of radiation going on. But there's no convection, because convection requires air or liquid, and it's a vacuum chamber, so there's none of that. So sublimation is the fancy word for the fact that the water skipped the liquid state and went straight from being a solid to a gas in the freeze drying process. Separate and different from the freeze drying process, we have vacuum drying. And vacuum drying just means you stick something into a vacuum chamber and the water boils off. So even though it's not heating up, it's not getting warmer, it's actually getting colder, but the water can either be boiled through heat or through reducing the atmospheric pressure around the water. So it goes the water goes from a liquid state to a gas state here, so you're not skipping that liquid state like you are in freeze drying. So I don't think that we're gonna need to freeze dry the filament. I think we'll be just fine just vacuum drying, just stick it in a vacuum chamber. But I can certainly try and stick the filament into my freezer before I stick it into the vacuum chamber. And the only drawback to doing it like that is I will not be able to have conduction because the filament's not going to be touching a hot tray. So I will have to rely on the heat radiating through the vacuum chamber onto the filament. And so that's going to be a very slow process. Okay, let's build this contraption. Well, this is one zany vacuum pump that I've got here. It is a rotary vane vacuum pump, so it should get a very good vacuum inside of that bucket. It sucks the air into this inlet, or there's another inlet there if I unscrew that, and it exhausts the air through there. I've already filled it up with the oil that came in the package, and yeah, it's plugged in, so all I have to do is basically turn that on, and I can feel the air being sucked into here or blown out of here. So this should work nicely. And now what I need to do is somehow connect the vacuum pump through this inlet to the bucket. And that's going to mean that I need to go online and order some more components. So let's order those components and draw up some geometry that will allow us to mount the componentry on the bucket here. Okay, here on eBay, this is the vacuum pump that I purchased for $50, $49.93. Then I got this vacuum gauge here, which goes from 0 to -1 bar, or -30 in mercury inches. This hose barb is what we will need to connect the tubing. Here's your tubing that I bought for 99 cents. And we'll get 2 of these valves. They're shutoff valves, so ball valves. So all told, $50 for the vacuum pump plus 20 bucks for everything else. So I'm into it. $70 so far into this project. This is the geometry that I've come up with to turn the bucket here into a vacuum chamber. Let's view this manifold in a semi-transparent state so we can see what's going on. You can see those internal, channels for the air to go through. And then these red things are basically representative of the 2 valves that we're going to put in. And this here is representative of the vacuum gauge that I need to install. I didn't draw them in detail because it's really not necessary. All I care about are these 2 bits of 3D printed plastic, and then these purple things here are those are the screws. So those are just drywall screws that will go through the bucket and hold the backing plate to the manifold. There will be obviously some silicone or some sort of gasket material in there to make it airtight. So let's get this printed and assembled. And here's what it all looks like when we put it together. So this hose will go onto the vacuum pump, just like so. Now this is compressible, so I'm hoping this doesn't collapse, but it probably will. But yeah, so there's my vacuum gauge. The air is getting sucked through here, through the bucket, and if I want to release the pressure, I can just spin this one and open it up as well. So that's open, that's closed on those 2 valves. And now I just need to drill the holes in the bucket and mount that with some gasket material so that it doesn't leak. All right, let's give this thing a test. Starts to collapse in on itself. This outer bucket here is meant to support it and keep it from collapsing, but we're at about, what is that, 0.1 bar, maybe, or 0.15 bar, and that happens. So this clearly will not work. Now at this point, I can probably guess what you're thinking. What an idiot. But hold on there, because this channel is called Design, Prototype, Test, not Design, I already have all the answers, I don't need to prototype and test. Thinking that this bucket might work, was not unfounded. I'd previously seen a woodworking video where the guy has this massive vacuum filtration system for his shop, and his buckets were collapsing because of all the suction from that vacuum. And by doubling up his buckets, he was able to keep them from collapsing. So I thought that I might be able to use that trick, but no, not even close. So what are my options now? Well, I can definitely build a box that's strong enough out of like 3/4 inch plywood. But what I'm trying to do is come up with a solution that will work for all of my viewers. And many of you don't have access to a table saw or other shop tools. So for you guys, I'm gonna try to find an off-the-shelf vacuum chamber that will also work for Filament. So let's jump on the computer and design the plywood box and also find a solution that you can purchase. This is a 3-gallon degassing vacuum chamber, and it comes with all of the hardware, meaning you're gonna save 20 bucks. So it's really $50 for that pot, if you wanna look at it like that. I've actually ordered one, but it's a bit of a risk because it doesn't tell you exactly what the mouth opening there is. Now, most filament spools are 8 inches, and I think that that gauge is gonna be a 2-inch gauge, so I think this is 10 inches, maybe even 11 inches across on the mouth of that chamber. So I think we're gonna be okay at $77. It's a bit expensive, but we saw what happened to the plastic buckets, so this is pretty much necessary. Either that or find the DIY plywood solution. And this is the plywood solution that I've come up with. So you're looking at an octagonal 8-sided box here made out of 3/4 inch plywood. You can see I've interlocked the pieces with this bird's mouth cut. And yeah, I think this will be plenty strong, all glued and screwed together to withstand the force of a full vacuum inside of there at sea level. Taking a look at the plan view, we can see that I was playing around with the 6-sided box or an 8-sided box. And the 6-sided box gives me less meat here to grab onto with the screw. You get a little bit more space there with the 8-sided box. And also, it requires the use of a 12-inch square lid, whereas the 8-sided box gets away with a 10-inch square lid. You can see those square lids there. And that's important because here on eBay, we can see that the price of a 3/4 inch, 10-inch square clear acrylic lid would be $25, whereas the 12-inch one would be $35. So $10 more. And yeah, so that's if you want to go with a clear lid that you can see through. And of course, I got that idea from this degassing chamber and every other degassing chamber that I've ever seen. But these are degassing chambers, which means that you want to be able to look in and see the bubbles coming out of the epoxy or silicone or whatever it is that you're pulling the gas out of. But we don't need to see inside of it. We just need to make sure that there's a vacuum, which we'll be able to tell from the gauge. And for that reason, I'm pretty sure we can get away with just a solid lid without a window in it. So I'm gonna make this whole thing out of plywood, and that means just using this drawing as a rough guide and getting to work in the wood shop. So let's leave the computer and go do some real work. All right, so I spent about an hour and a half getting this far. As you can see, I've made the whole wall assembly, which is the hard part. And for anybody who wants to build this, I will flash on the screen right now the dimensions that you will need to cut out on your table saw to make this shape. But I don't think I'm gonna continue with this. And let's talk about the reasons why. So this is 1/6 of a sheet worth of plywood. So that's $10 worth of plywood, but you have to buy the whole sheet, which is about a $60 sheet here in the Pacific Northwest where I live. So that's not cheap unless you already have the plywood sitting around, in which case it's free. On top of that, you're gonna need some silicone caulking. That's like a what? I don't know, $5 to $10 tube right there. You'll need $5 to $10 thing of paint. This is latex paint, which you'll need to seal all the plywood. You'll need to get a $1 brush, maybe a $5 bottle of expanding glue that will expand in the joints but also glue the joints together. So that's how you'll keep it airtight. And of course you'll need to get the hardware that we already talked about in the video here, which is the vacuum hardware. So all things told, you could easily be above $75 just to make this project happen, unless you're like me and you already have all of these things sitting in your garage waiting for the next project. But you still have to consider your time, right? Your time is worth something, and it's just so much easier to buy the $75 pot, which comes with a better gauge. This is a fluid-filled gauge, so it's superior to this other one that I bought. And it comes with all the hardware, and the total cost on this is $75, and it's metal, and it's just, it arrives and it's pretty much ready to go. So let's get this thing assembled. Shouldn't take a minute, and then we'll talk about it, and then we'll do a test run with it. And that's all there is to it. You attach the hose to the vacuum pump and to this bit of hardware here that comes all pre-assembled. Then you attach the hardware to the lid and you're done. Now I do have to say that my lid came with a deep gouge in it, but it shouldn't affect, it's here in the middle, and I'm hoping it won't affect the ability of the unit to hold a vacuum, but we'll see. We'll have to test that. So yeah, this vacuum chamber is the perfect size for the normal 8-inch spools of filament. You can fit 4 of them stacked in there. And you can see that these are a lot of wide rolls of filament, and they come right to the very top of this, but they do compress a little bit, and so I think that my lid will work just fine. Yeah, I think that'll work. Yep. So, let's try it. Okay, I gotta tell you guys, that's kind of scary, just the noise that the vacuum pump makes, but once you close the valve, it really quickly gets to a vacuum. So I'm currently at negative 0.8, so I'm almost to a full -1 bar, and we'll just turn this on again. I'm just gonna leave it there. That's at a full -1 bar. And if you'll notice, this exhausts a lot of, I don't know what it is. Maybe that's the air vapor, maybe that's oil being misted. I don't know how, but don't ask me what's going on, but that is fully at vacuum, and I've shut off the 2 valves, which means that theoretically I could detach this from the vacuum and let this sit like it is. And apparently, according to other users in online forums, this will hold this vacuum for days and days. So I no longer need to turn on the vacuum pump. It's just those, 30 seconds that it takes to suck this down. So an ideal filament storage solution might be to get a bunch of these $75 pots and store four rolls a piece in each of these pots. Here's how I'm going to test vacuum filament drying using this system. This is a old roll of ABS filament. I got this from GearBest last year sometime, and you might recognize the color. This is the material that I used to print up all of the parts on the food dehydrator filament dryer that you were seeing earlier. And so it's currently very waterlogged. It's been just sitting out in the air. You can see how easily it breaks even because it's so wet. So we're going to do a test print with it. We're going to print a single wall vase here on the Ender 3, and then we're going to stick it into the vacuum chamber for maybe 6 to 12 hours. And every 6 to 12 hours, I'm going to remove it, do a quick test print, and stick it back in the into the vacuum chamber. And we'll see just how long it takes to get this stuff dry and just how well it does dry out. Let's illustrate what's happening inside the filament. So there's the vacuum pump. Here's a glass of water. We're just going to stick that in the chamber here and then pull a vacuum on it. The vacuum pump is turned off. You can see we have that much vacuum pulled, almost a full bar. And yeah, the water is boiling. You can see those bubbles coming. Now if I turn that vacuum pump back on and really pull that strong vacuum on it, it really boils in there. Look at it go. That's a vigorous boil. Okay, so I'm going to turn that off, and then I'm going to let all the air out of the... And now you can see that the glass is fogged up, and I can just stick my hand right inside the water, and it's cold. It's actually colder than it was when I first put it in there. So That's what we're doing. We're basically cold boiling the filament to get the water out of it. And that's why it's such a gentle process. So this here is the undried filament, as wet as it gets. And you can see just what an ugly print it makes. The 0 there for the 0 hours that it was dried. We can see I'm getting some stringing here on the first layer, which means I'm having layer adhesion problems with the, or bed adhesion problems, I should call it. There in the mouth, you can see the stringing that occurs, and on the sides, you can see these, I don't know what to call them, dribbly bits. So basically, it's all the same problem, right? And the roughness of the skin. So there's no shine to it. It's kind of a matte look, and I think you guys can see that in this macro photography close-up that the extrusion is just really not smooth. And like I said, all these problems caused by the same factor, and that is the water inside the filament is boiling as it passes through the hot nozzle, and that expanding gas, the boiling water in the gaseous form, is pushing more filament out of the nozzle than what the extruder is trying to push out. And not only that, it's pushing it out irregularly. So yeah, wet filament is a big problem. Now, here we have one that I have marked with an 8, and that means because I left it in the chamber for 8 hours, but that 8 hours is not an accurate number. And that's because my vacuum chamber is losing pressure, and as time went on, it was losing pressure more and more rapidly. And I don't know if it was held under a full vacuum. I don't have any idea how much time it would take to really get these drying results, because this might have only been dried at full vacuum for an hour. So this might only be a 1 hour difference. But yeah, looking at these two prints, you can start to see a big difference. This one here is much more shiny than the original, and the surface finish looks quite a bit nicer. There's fewer sort of dribbly bits. We do still have them like up here at the top, and the stringing is less severe, and that's going to be more and more the case as time goes on. So this is a supposedly 20-hour drying time, and I did suck down a full vacuum on this twice, I think. So yeah, we can just kind of see the progression. It's getting nicer and nicer. And finally, we have this one marked, 35 hours. Again, I sucked down the vacuum 2 or 3 times on this one. And yeah, real nice shiny surface compared to this original. And we're almost done getting stringing, and there's only one small moment there with a little bit of like a dribble that caught on the print. So clearly, this technique works, and the only issue that I'm having is keeping the chamber fully evacuated. Now, this one here still is not dry. When I passed the filament through the nozzle by hand at this stage, I was still hearing the snap, crackle, and pop noises that tell me that this filament is nowhere near being dry enough. So still quite a bit of improvement to go with this at this level, and you can see already how much better it looks than the fully wet filament. So there is a lot of promise in this technique, but let's talk about the problems that I'm having with the vacuum chamber. You pay for what you get, right? And I got this whole vacuum pot for $75, which is as cheap as you can possibly get it. And this one that I got, I received it with this big old scratch, and hopefully this will come through on camera. But there's this huge scratch that goes from there all the way to the other side. And unfortunately, it's right through the middle of where the hole is. So that scratch could be the ingress point, or actually, yeah, the ingress point for air from the outside. Now there's this silicone washer here, and there's one here on the backside as well. So hopefully those are squishing well enough to fill in the crack, but it's very possible that that's where my problem is coming from. I think the more likely problem is actually this gasket here, which seals quite nicely, and it's nice because it's two-sided, so if you ever had damage happen to this side, you can just flip it around and use the back side here. But silicone is kind of strangely sticky. I mean, we've all held silicone before, right? What I think is happening is I've got some dust. I use my garage as a wood shop as well, and I mean, I've tried to clean it, but I think that no matter what I do, there's going to be a little bit of dust. And so this seal is just not sealing as perfectly as it could to the rim of the pot here. So this system, as I currently have it set up, is not ready for prime time. But in the course of making this video and doing this project over the last several weeks, I've learned a whole lot about filament drying, and I'm going to give you some of those lessons learned. But before I do that, I need to give the usual giant thank you to my monetary supporters. These guys make these videos possible. So this is a small channel. I earn very little money from YouTube ads, and therefore I depend on these guys. So thank you so much if you're one of these guys. And if you're not, please consider joining their ranks. The link is in the doobly-doo. All right, so lessons learned. First of all, we need to be able to control the vacuum on this apparatus without having to do it manually. In other words, I come in and check on it every few hours and just turn the vacuum switch back on and suck the pressure back down, but it does lose vacuum, and I think that's pretty much unavoidable with age. Probably mostly just because of the dust on the silicone, which I've tried to wipe off, but you know, it just, I don't know. Something in there, the scratch that you guys saw, for some reason, it's never gonna hold that vacuum continuously. There are solutions that might, like the pressure pot from Harbor Freight that some people swear by, but I think that eventually when those things get a little bit worn, you're gonna have the same problem. So the real solution here is to use a vacuum pressure switch that automatically turns on the vacuum pump here whenever the vacuum pressure drops above, not below, but drops above a certain pressure. So yeah, those vacuum switches are surprisingly hard to come by. Most of them are for about half of the vacuum pressure that we need. So I want it to basically trigger at about 0.95 bar, or negative 0.95 bar. So I'm gonna do some more research and try to find a vacuum pressure switch that will work at that rating. But I might have to DIY my own solution. So that's going to be a future video where I finalize this system so that whenever the pressure's in the wrong spot, it will kick on this compressor, or the vacuum compressor? The vacuum pump. So yeah, that's the future of what I plan to do. But this is getting pretty involved, you guys. You know, you got the $75 pot and the $50 vacuum pump, and then we're gonna have that switch. So we're looking at almost $200 by the time, if I bought a vacuum switches are like anywhere from like 50 to 150 bucks for the ones that I'm finding on eBay. So yeah, it could be a really expensive project. It is, of course, I still think the best way to dry your filament. It's the least sort of aggressive, or it's the lowest impact way to dry your filament. So like it would work really well with wood fill PLA, for instance. Now, PLA does not soak up the moisture from the air really that noticeably. You can pretty much just print with PLA after you leave it in the air. But wood fill, the wood fibers themselves do soak up the moisture, and so then they have all the problems of wet filament. And so you want to dry those wood fibers without heating up the PLA, because heated PLA is annealed PLA, and annealed PLA has different characteristics, and so it's much more difficult to print. In fact, I've never successfully printed with truly annealed PLA. And how did I find out about this? I dried my PLA in my little filament dryer, the dehydrator, and it annealed on me, and I could never get a successful print out of that filament again after I did that. So you really don't want to bake your PLA at even, 150 degrees Fahrenheit. So maybe 100 degrees Fahrenheit, so whatever that comes out to in Celsius, might be okay. The vacuum drying of PLA and wood fill PLA is the way to go. There is another solution, and this one's very interesting. There was a YouTuber by the name of Rich Rap. Now, he's no longer making videos. It's kind of a tragedy because he was really talented. He's the guy that was responsible for for trying to get the replaceable spool. So you just have the plastic spools that you would 3D print or perhaps buy, and when you bought filament from filament manufacturers, it wouldn't include the spool. And what a great idea, right? And unfortunately, that hasn't taken hold in the market. But another very clever thing that he came up with is the way that he dries his filament. So he basically has a big Tupperware box, like from IKEA or something like that, and he puts a little low temperature heating mat. So we're talking 20, 30 degrees warmer than the ambient air. So really not that warm, but he's always got this box at a slightly higher temperature than the air, which means that the filament stays dry inside the box. And if I remember right from his video, it didn't use all that much power. So I think bang for your buck, Rich's solution is probably the best way to go for most of us. You just have to make sure that your filament is always kept on the shelf in that box, and you never need to like dry it in like a day or two. Now, I still think that this will dry filament rapidly if I can keep it at that negative pressure for quite a while. You guys saw how vigorous the water boiled. So at those very extreme vacuums, almost a -1 bar, the water really does want to vaporize. So as long as I can keep this at that vacuum, it's probably only going to be like a couple of hours to dry filament. That's what I'm hoping anyway. So further experimentation clearly is needed, and until then, I'm going to keep using my food dehydrator to dry filament. The last thing I want to talk about is this polycarbonate filament. Now, most of you are probably not printing with polycarbonate. It requires an all-metal hot end, and you also have to use a thermocouple or Slice Engineering sells an advanced thermistor that will allow you to get to those higher temperatures, 310 degrees. I made a video, you can go watch it, about modifying not this printer, but my other Ender 3 printer to print at 310 degrees for polycarbonate. So most of you, this doesn't matter, but for me and anybody else trying to get into sort of really engineered plastics and making really engineered parts out of these printers, polycarbonate will soak up air out of, or moisture out of the air in a day, like 24 hours. So I can pull this out of the dehydrator. It's been sitting in the dehydrator for 3 days, just bone dry. I will do one print and it's fine, and I leave the roll on the printer, come back the next day, and it's already like as bad as it gets as far as moisture from the air. So just crazy that it does like that. So you either have to keep this in a sort of enclosed spool, so no open spools like this, so that it's not really ever getting dry, or you have to be able to dry it quickly, or, so I still think that this vacuum chamber has a lot of promise, and it will be a better solution than sticking your filament into an oven or even a food dehydrator, in the end. All right, well, that's it for this video. Thank you very much for watching, and I will see you next time.